So, let us take up this Lagrange simplified equation for finding shape function. The general procedure which I told for finding the shape function, that is in the usual way, first choose the displacement in the polynomial form, then apply that equation to various nodes and express that polynomial form, that equation in nodal displacement term, then find the inverse of that coefficient matrix, then arrive at the shape function. That's the general procedure. But it looks tedious, so this is one of the shortcut method wherein you will find only one equation available for finding the shape function. The general equation for finding the shape function at any point, suppose this is applicable for finding the shape function only along rectilinear orthogonal lines. That is one important thing, limitation. It is having. That is Lagrange equation. It is applicable only for a rectilinear line. So that is either horizontal line or vertical line. Or it may be normal to these two, only orthogonal lines, only one direction. Suppose you have a line here like that, say, like that. So this is one node along that line, second node, and another any node in the middle, ith node. So just left side of that ith node, it will be I minus 1 node. Right side of that ith node is I plus 1 node. One after that, one numbering. And this is the last node, n. So there are n nodes along the line, either in the x direction or it may be in the y direction, exactly orthogonal to that. Not inclined, it's only one line at a time. Right? If it is orthogonal in xy direction, like rectangle, well, it can be applied by taking both, multiplication of both, you can do it. Tensor multiplication of x direction and y direction you can take. So for line elements in two directions, x, y directions, and for planes which are rectilinear plane, you can apply rectangle, square, you can apply. Not for quadrilateral direction, but isoparametric concept you can use for even quadrilateral also. If you use that isoparametric concept, if you say we are using isoparametric concept, that is same shape function you will apply for x present nodal coordinates also. That concept, if you take it, then well, it can be applicable for quadrilateral also. That's it. And by integrating, differentiating, you have to use partial tensor application, that is partial derivatives only you have to use. And you have to use Jacobian for finding the interrelationship between the natural coordinates as well as global coordinates. You have to use the Jacobian transformation, not the regular thing. Jacobian transformation only you have to. That's only for isoparametric element theory. The relationship between natural coordinate and Cartesian, global coordinate, Cartesian coordinates, it is only through Jacobian. So you have to use that, or Jacobian transformations you have to apply. So suppose you have a line like this. Suppose you want to determine the shape function at any point, either it can be in the Cartesian form line or it can be in the natural form. Suppose I will take this is natural coordinate psi eta. Instead of x, y, I will take psi eta as the natural coordinate. Right? They are the natural coordinate. So n shape function at any point I, it is given by psi minus psi 1 into psi minus psi 2, where psi 1 is the natural coordinate of node 1, psi 2 is natural coordinate of node 2. Like that. Psi minus psi I minus 1 up to I minus 1, what all the other nodes, excluding the ith node. Don't take I out thing. The next thing will be I plus 1. That ith node is missing. You can observe that in that equation. Like that. Psi minus psi n. If it is global coordinate x, this was then will take x. And x coordinates only. X minus x1, x minus x2, like that. If the Lagrange equation, if you are taking for an element in Cartesian form, then you use the variable as x. If it is in the natural coordinate form, you use the variable as psi. That's all the change. And this entire thing multiplied by psi coordinate of the point under consideration. This psi, we are writing shape function for ith node, n1, n1, n2, n3. Shape for number of shape functions will be number of nodes. 2 noded element, 2 shape functions, n1, n2. 3 noded element, 3 shape functions, n1, n2, n3. It depends upon them. How many shape functions will be there means as many number of nodes as there in the element, you have that shape function. You take the shape coordinate of that ith node number. Here ith node is missing, that you can take care in the numerator. Now ith node, from the ith node, subtract all those whatever you have in the numerator. Psi I, psi 2, psi I minus 1, psi I plus 1, like that, psi I minus psi. That's all. This is the simple formula. You need not have to bother about inversion and all those things, as you have the general procedure for finding the shape function using Lagrange form. Right? One is this formula, you do remember, wherein the numerator consists of only the general variable, either psi or x, depending upon global form you are applying shape function in global form or shape function in natural coordinate form. Depending upon that, you select that variable, and from that variable you subtract the coordinate of all nodes in the numerator. Denominator, that same subtraction will be from the nodal coordinate. That's all. But this, if you remember, is very simple process. Whether it is in one direction, second direction, another direction, orthogonal. So if it is in the eta direction, then use is one side eta. If it is exactly orthogonal direction, eta direction, replace z by eta. Okay? Then if it is two-dimensional, perfectly orthogonal, rectilinear, then takes tensor product. This into this. That's all. Ni, n, eta. Eta, you have to take. That's all. That function, whatever is there, that you have to use. Anyway, so this is the formula we are using. Now we will take up examples straight away. I will take some examples, small examples, then it is better understood. Is it clear now? Limitation is, it is applicable. Here only we will continue in the same thing. We don't change it. Let's continue in the same thing. So now, example. First, find shape function, shape functions for nine element, that is primary element in natural coordinates. So it is this line element, correct? Huh? So this line element has two coordinates. So I told it is in natural coordinates. So natural coordinate origin will be at the center. That you know, already I explained natural coordinate, local coordinate and global coordinate. Global coordinate at any point in the region. Or in local coordinate, it will be only one node. In natural coordinate system, origin will be at the center. So if this is length L, this is L by 2, L by 2. Already you know the shape functions are 1 minus psi by 2, 1 plus psi by 2. Already by inspection, I have already used. Now I am deriving that. Consider this element. So from this, I will know. So how many shape functions will be there? There are two nodes, so two shape functions. So you write for here, natural coordinate. What is psi here in the natural coordinate? Because this is the origin. Length has to be 2. This will be minus 1. Here, psi will be plus 1. Coordinates. Natural coordinate system. Natural coordinate for node 1, psi equals minus 1. If it is global, whatever x coordinate, that you take. That's all. Very simple, straightforward thing. Nothing other than that. So N1 is equal to psi 1 I have to leave. Observe, I have left. I have told here, one coordinate don't bother first. When you are writing shape function for I, leave that. Psi minus only psi 2 I have to take. Next only. When do you leave it? You see this. For writing shape function for I, we are taking I minus 1, I minus 2 and all those things on left side as well as right side nodes. Here, only two nodes. I am writing shape function for 1. There are no left nodes, other left side nodes. Only one node on the right side. Only one node. Clear? That's all you have to remember. It is simple, straightforward thing. Only there should not be any confusion while applying the formula. Divided by psi is of course psi 1. I am writing for 1. And this psi 2. Something. That is psi minus, what is psi 2? 1. Here, psi 1 minus 1. One that is known. Coordinate is known. Then this is minus psi 2 plus 1, whatever is there. Minus that. So this is psi minus 1 by minus 2. Or it is 1 minus psi by 2. This is exactly what you got. Even if you adopt that general procedure, taking the polynomial as u is equal to alpha 1 plus alpha 2x. If it is in the natural coordinate system, alpha 2 psi. Right? So here you have U1, here you have U2. U is at any point, is this, then apply at, this is in the form 1 psi alpha 1, alpha 2. This is phi, this is alpha. Correct? Apply this to two nodes. At node 1, U is U1. Z is minus 1. So you will get alpha 1 minus alpha 1. Alpha Z is minus 1. So it is alpha 2. Then again apply at node 2. You will get alpha plus alpha 2. Z equals plus 1 then. So this you can write it in matrix form. Right? This is 1 minus 1, alpha 1, alpha 2. This is your U matrix, this is A matrix, this is A inverse. Right? A inverse, therefore alpha is A inverse Q. This is Q, nodal displacement. I don't call it U. So what is A inverse? This inverse is 1 over determinant 1 minus of minus 1, 2. Correct? 1 minus of minus 1. Determinant 1 over delta into transpose of n. This. So this coefficient is 1. So then minus this coefficient is minus 1, that is right there. This coefficient is minus 1, 1. Into Q. This multiplied by pi, one side, into half into 1 minus 1 into that U, Q. Correct? So you this, if you do it, this is half 1 into 1. 1, then minus Z. Then this is minus 1 into minus 1. 1 into 1, 1 into minus 1, 1 into minus 1, that is minus 1, and then say, I think this you check, this is 1, okay, then this is 1 into 2. So it is 1 minus I by 2, 1 plus I by 2. Into 2, N1 into the two share function. N1 is 1 minus I by 2. So this is by your general procedure, writing the polynomial form in terms of the variable, then substituting in nodal coordinates, get it, and writing it in the form like this. Q equals A alpha, then finding the inverse, then multiplying by that, substituting that alpha here, getting the shape. That is your general procedure. Here, straight away, you get it. This much workload is not there. Here, straight away remembering this equation is also very simple. Especially for two-dimensional things, this becomes easy. Because this involves two variables. Inverse, again, lot of things. I hope anyway, one problem I will work by this method also, it will be very clear to you. So, you can write N2, it is 1 plus I by 2, we will see that. N2 means this 2 I have to forget. because here psi is not there. 2 forget it, only other node. So psi minus psi 1, only 1, no other nodes. Divided by, this will be psi 2 minus, that is that node. So it is psi minus of minus 1. Psi minus of minus 1. This is psi 2, 1. This is again minus of minus 1. So this will be psi plus 1 divided by 2. 1 plus psi by 2, 1 minus. See how simple it is. This is called Lagrange equation for finding the shape. I told you limitations. This is applicable only for line elements and rectangular elements or square elements. Right? Rectangle or square. Again, higher order in that rectangle and square, if nodes are present only along the boundaries, you cannot apply. If it is in the middle for 9 node and rectangle, then you can use it. Like that, 9 node you can apply because nodes are similar along x and y direction. Suppose if it is 8 node and rectangle like this, then you cannot use because along this 3, here middle, only 2. You cannot this method face. Right? That's all. And how to do this means? For this you have to go for usual method. But I will give you shortcut method. And once we know this, then we can write by inspection as it is. I will indicate it because some more problems I will work in all those things. Is the problem, that's why already I told, problems I will work from next class onwards. So while working the problems, for all the elements we will write rectangle, higher order, then isoparametric type, all those things we will write it and do it. So, is it clear now? We take now second example. No, so you find shape function for 3-noded element. This is called quadratic element. This is linear element. This is also called as linear finite element. This is called quadratic line element. If you have one more node, 4-noded cubic line element. See, degrees of freedom are varied. So shape function also varies. Simply one dimension means it is not constant. For the first time number, first n nodes, usual practice, primary element. Then third node. For this, I will write n1. How many shape functions? 3 nodes, 3 shape functions. n1 equals, what to forget it? What is xi here? First coordinates I'll write. Again, this I'll write for natural coordinates. It may be Cartesian also. Both same equation can be applied, but only of xi to take x or y in whatever direction. So n1, this is psi minus psi 3, psi minus psi 2. Correct? Numerator. Forgetting this, other 2 nodes divided by, this will be psi 1 minus psi 3, psi 1 minus psi 2. Denominator, same thing, we have to subtract from the 1 for which we are writing. Write the coordinates. Psi, this, what is the, here psi equals plus 1 in the natural coordinate. This is center point, center node, center point. If this node is given here 1/3 distance from left, z minus z equals minus 1/3. If it is at 1/4 point, z equals minus 1/4. Like that, where that internal node is there. So here quadratic means exactly another one middle node will be in the center. Correct? Next I will take one more cubic. At that time, I will take it 1/3 point. 1/3, 1/3, 1/3. Middle third. That's all. How to place the node, any place. This is exactly center, so that equals 0. Right? That's why this Lagrange shape function is a shortcut method I told you. You can write easily. So here psi 3 is what? 0. Then psi minus psi 2. Psi 2 is 1. Psi 2 is 1 divided by psi 1 is minus 1. Minus 1 minus 0, minus 1 minus 1. Correct? From the Lagrange one. Or this you can write it as psi into psi minus 1 divided by this is minus 2 into minus 1, that is 2. This is minus 2 minus 1 plus 2. This is this is the 1. Then 1 psi into psi minus 1 by 2. You remember for one linear element 1 minus psi by 2, 1 plus psi by 2. Here you can say minus psi into 1 minus psi by 2. If you want to remember this same shape function into minus psi, that is the one for quadratic. So then either way you can write it out this way also. Write it. So n2, this node. So it will be psi minus psi 1, psi minus psi 3 divided by psi 2 minus psi 1, psi 2 minus psi 3. Correct? So this is nothing but psi minus of minus 1. Psi 1 is minus 1. Minus of minus 1 into psi minus psi 3, 0 divided by psi 2 is 1 minus of minus 1, then 1 minus 0. This is nothing but psi into psi plus 1 divided by this is 1 minus of minus 1 plus 1. 1 plus 1 is 2. This is that. Here it is psi into psi minus 1 by 2. Here psi into psi plus 1 by 2. Then n3 shape function. n3 is psi minus psi 1 into psi minus psi 2 divided by psi 3 minus psi 1, psi 3 minus psi 2. Correct? So this is nothing but psi minus of minus 1, then psi minus 1 divided by 0 minus of minus 1, 0 minus 1. And once you write the numerator, denominator the same thing. So this is psi plus 1 into psi minus 1. Denominator, it is 1 into minus 1. Minus. So this is n squared minus 1 divided by minus 1. I can write it as 1 minus I square. Because this will be I square minus 1. Then divide by minus 1. Minus 1, I will write 1 minus I square. Instead of I square minus 1, that minus I will take it inside. It is 1 minus I square. Now we can remember this shape function for quadratic element. It is z into z minus 1 by 2 for n1, z into z plus 1 by 2 for n2, n3 is 1 minus z square. Clear? This is the procedure. Like that, you can try for 3 node. I will take 3 nodes afterwards. Now I will take one problem on rectangle so that is easier to use. Either rectangle or square, whatever it is. Always I will take natural, but Cartesian also can be applicable. Similarly, it can be applicable, I told you. So this is center point. This is how the natural coordinate of a two-dimensional, because in the syllabus it says two-dimensional also. Lagrange shape function or two-dimensional. It's only one dimension, others. But shape function, when they told Lagrange equation, they say two-dimensional, one word is there. So that's why I took this, so that it completes everything. Next class, only problems will work. Go on working. All this theory, whatever I have told, based on that, I'll work problems. Maybe 1 or 2 classes, or depending upon if I work more problems, more classes, that's all. Nothing other than that. So I will take a rectangle element. For this, what are the coordinates? minus 1, node 1. Always numbering node, you have to number it in anti-clockwise direction, preferably counterclockwise. That's why moment also I told we'll take anti-clockwise in finite element. Right? Otherwise it leads to negative, positive confusion. So here, this coordinate, it is 1, minus 1, 1, 1, minus 1. X, Y coordinate, or Z, eta coordinate. Parent element, or it is natural element, primary element, having nodes only at the corners, not higher order, first order, basic, finite element for useful two-dimensional analysis. So for this, already I told you, whatever we had here, in both directions we have to use it and take the tensor product. Along side direction, it is takes first node 1, then 1. How to write, I have explained. Watch carefully. 1 node along side direction. You have a member. This is left node of this side direction. This node 1, it is common for 1, 2, 1, 4 sides. 1, 2 side is in z direction, 1, 4 is eta direction. You have to take tensor product corresponding to that. You have to remember those things I told you. So for 1, 2, this is the left node. That's why numbering should be in the anti-clockwise. Always this is first, this is second. That you have to be careful. So whatever n1 is there for side direction. What is n1 for side direction? 1 minus a by 2. Correct? Huh? Is it clear now? Clear or not? So for node 1, this is 1 minus a by 2. Along eta direction. Again, it is first node only, 1, 4. This is first. Again it is 1 minus eta by 2. Correct? It is. Or shape function. See? N1 is 1 minus I by into 1 minus eta by 4. Very simple. That's why for two-dimensional thing, they told in while doing this Lagrange equation in the syllabus. Same thing, nothing other than that, it's the tensor product. Then N2. Or the other way also you can see, this is Y is negative, Y is eta also negative, that negative you take it, divide by 4. 1 minus A, 1 minus eta. So N2, come to N2. 2 node is common for 1, 2, 2, 3. For 1, 2, it is second node. 1 plus Z by 2. For this, it is first node. 1 minus eta by 2. So this will be 1 plus Z by 2. This is 4. See how simple it is. This is how, you need not bother about your usual procedure, but that is the general procedure you have to follow, because always we don't idealize the things using only rectangles, using only lines like that. Any shape means isoparametric we have to go naturally, irregular shapes is the isoparametric concept and this. So likewise, in 3, it is for y direction 3, 4. Right? It is again, with 3, 4 means it is opposite, but we have to take y direction here. We have to see with reference to this. This is the positive direction of the element. Element we have to see. So here this is negative, second node. Like that also we can see. Second node, 2, 3. But in the clockwise, that's why I told you anti-clockwise only, you have to see numbering. Here if you go for numbering this will be minus of minus 4, we have to take it, we have to bridge it the other way. You have to be very careful there. So this N3, both are positive. And likewise, N4, 1 minus psi. Now we can write straight away. First quadrant, second quadrant, third quadrant, fourth quadrant. Here both psi is negative, eta positive. Both are positive. Here psi positive, eta negative. That you know, first quadrant, second quadrant. Using that. But this is by Lagrange. Third node especially. It is second node of this line element. Always you have to go from right to left, positive. This is positive side. Otherwise, negative you don't take it. So this is how we can write shape function for two-dimensional figures. Or likewise, 9-noded also you can write. If you have 9-noded here and 1 node, same. You remember that quadratic element. This is 1 z into 1 minus psi by 2 node. For 9-noded, N1 if you want to write, this is z into 1 minus psi by 2 for this eta direction. That's again lower first node only. Correct? Eta direction, first node only. Zeta direction also, first node. So this will be eta 1 minus eta by 2. So this will be psi eta 1 minus psi into 1 minus eta by 4. Likewise, n2, n3, n4. When you come for n5, 1 minus psi square, along this eta direction, it is first node. Correct? For this, suppose if you take this fifth 1, 2, 3, 4, fifth node. For eta direction, it is middle node, 1 minus x square. For eta direction, first node, xi into, not xi, eta into 1 minus eta by 2. When you take this is xi, middle node, eta also middle node, 1 minus x square into 1 minus eta square. I hope I made the point clear. Higher order also becomes very, very simple. I need not have to bother now. The moment I told Lagrange shear function, that first step of finding the element constant shear function, it becomes easier for problem solving. Shear function. That relevant strain displacement matrix you can take it. The moment you get the shear functions, u at any point is n into nodal displacement d. Then take appropriate strain equations, write the matrix, d matrix, then find step. That's all the procedure for element properties. I hope I made the things clear. From now onwards, it's only problems like this. Now I have solved line element and quadratic line, cubic also, told same procedure. You can keep it as a homework, otherwise I will solve next class. You can remember the basic elements, line elements, right for two-dimensional rectangle with symmetric 9 noded already I have told, 4 already I have told, 8 noded I will tell you, and likewise other nodes also can write the shape function. But three-dimensional you can forget it, it is not there in the syllabus. Only 1 and 2 elements. What are the things which are there in the table, family of finite elements? For all those, remember shape function. You have to remember shape function. Then you can write strain displacement, constitutive matrix, and stiffness. Then you use that in problems.